At low Reynolds numbers, Re1, the world of fluid flow is supposed to be calm and predictable. In this regime, viscosity dominates, inertia is negligible, and streams of liquid slide past each other without ever tumbling into chaos. The flows are laminar, smooth like layers of silk, and mixing should be painfully slow, driven only by molecular diffusion. Stirring a droplet at this scale should feel as hopeless as trying to blend cream into coffee without ever swirling the spoon. So how is it that, in the micro and nanoscale world, we often observe droplets mixing with surprising vigor? Doesn't it seem paradoxical that turbulence-like behavior can appear where turbulence is forbidden? The answer lies in hidden drivers that exploit interfaces. One such mechanism is the Marangoni effect, gradients in surface tension, caused by temperature or concentration differences, set up flows along the droplet surface. These surface currents sweep the interior liquid into vortices, churning and folding material far more effectively than diffusion ever could. A tiny temperature gradient of just a few degrees, or a concentration gradient from a dissolving solute, can unleash vigorous circulation. It is as if the droplet, perfectly laminar in bulk, hides miniature engines at its skin. Isn't it fascinating that surface stress becomes a substitute for turbulence at small scales? Another driver comes from vapor and solute flows. When droplets evaporate, vapor leaves unevenly across the surface, generating microflows inside. If solutes dissolve unevenly, similar gradients create strong recirculations. These flows can trap particles, sweep dyes into striking patterns, or even generate chaotic advection inside a millimeter-sized droplet. Experiments have shown coffee rings forming from pinned evaporation, or convective rolls stirring the droplet interior as if invisible stirrers were at work. Could it be that evaporation itself, often dismissed as simple, is one of the great hidden mixers of the micro-world? A lesser-known insight is that these interfacial mixing effects are not just curiosities but practical tools. Engineers designing lab-on-a-chip systems deliberately exploit Marangoni stresses to stir reagents, accelerate reactions, or homogenize analytes without moving parts. In biological contexts, sessile droplets can generate mixing that helps concentrate biomolecules or nucleate crystals, shaping outcomes in ways classical fluid mechanics never predicted. Mixing without turbulence is not only possible, but in many cases superior, because it is tunable by chemistry and interface design rather than brute force. Doesn't this suggest that laminar flows are not limitations, but opportunities for new physics? The paradox, then, is that laminar worlds, supposedly condemned to sluggish diffusion, can display surprising and efficient mixing, driven by forces that live at interfaces. Out of smooth flows come hidden vortices. Out of evaporation and gradients comes order and motion. The haunting question is whether this kind of non-turbulent turbulence is a special feature of droplets, or whether it reveals a deeper principle, that nature always finds a way to stir, even in the calmest waters. In microfluidics and small-scale systems, the Reynolds number, Re, is far below 1. At such low Re, inertial forces are negligible compared to viscous forces. This makes flows laminar, with fluid layers sliding smoothly past one another. Classical theory predicts that mixing is extremely slow, relying only on molecular diffusion. No turbulence is present to stir the system. As a result, low Re flows should resist mixing and preserve sharp concentration gradients. Diffusion-limited transport defines the laminar world, yet experiments often show vigorous mixing even under these conditions. Food coloring in honey diffuses extremely slowly, remaining as unmixed streaks without agitation. It is like pages of a book sliding past each other without ever shuffling the words together. Despite laminar predictions, sessile droplets and confined microfluidic systems display strong internal mixing. Circulatory flows arise that stir solutes far beyond what diffusion alone could achieve. Mixing occurs on timescales orders of magnitude faster than theory suggests. This contradicts the expectation of stagnant or layered flows. Instead, droplets often display vigorous convective patterns. This reveals hidden drivers of motion, even at low Reynolds numbers. The paradox is that laminar systems act turbulent without turbulence. Mixing emerges where none should exist. Sessile water droplets with surfactants mix dyes within seconds, despite Re1. It is like a calm pond, suddenly swirling with hidden currents. A major mechanism behind unexpected mixing is the Marangoni effect. Surface tension gradients caused by temperature or concentration differences drive strong flows along interfaces. These surface-driven flows penetrate the droplet interior, stirring contents. Even small gradients can generate persistent vortices. This introduces active mixing in systems predicted to be diffusion limited. Marangoni stresses exploit interfacial energy to move fluid. Instead of passivity, droplets become dynamic mixers. Surface physics overrides bulk laminarity. Alcohol evaporation at the edge of a droplet induces Marangoni flows that rapidly mix its interior. It is like pulling on a tablecloth. The whole set of dishes moves with the smallest tug. Another driver of mixing is evaporation. As solvent leaves a droplet, solute concentration gradients form near the interface. These gradients create density differences, which in turn drive solutol convection. Vapor pressure variations also induce asymmetric flows. The droplet interior circulates in response, mixing solutes far more effectively than diffusion. Evaporation transforms sessile droplets into self-stirring reactors. This effect intensifies as droplet size decreases. Evaporation thus bridges laminar flows with vigorous mixing. Coffee stains form ring patterns due to solutal convection inside evaporating droplets. It is like a melting ice cube driving currents in its own glass of water. Marangoni and evaporation effects generate vortices inside droplets. These vortices act like tiny stirrers, continuously circulating liquid. Flow visualization reveals toroidal rolls and spirals inside droplets that appear still from the outside. Such flows persist as long as surface gradients remain. They redistribute solutes, mix reagents, and influence crystallization. The paradox is that low re-environments contain rich internal structure. Laminar does not mean static when interfaces are active. Droplets become micro-mixers hidden in plain sight. Fluorescent tracers in sessile droplets reveal complex internal vortex networks under evaporation. It is like wind swirling invisibly inside a glass dome. Temperature gradients amplify mixing through thermocapillary Marangoni flows. Solitol gradients from differential evaporation reinforce this effect. Together, thermal and concentration fields couple into strong interfacial stresses. These forces are nonlinear, producing unexpected mixing even in symmetric droplets. Localized heating by lasers or substrates further intensifies flow. Microfluidics exploits such coupling for controlled stirring. The paradox becomes a tool for design. Laminar worlds host hidden engines, powered by gradients. Laser-heated droplets develop strong circulatory flows for nanoparticle assembly. It is like sunlight focusing through glass to set air swirling. Vigorous mixing at low Re overturns assumptions in microfluidic design. Engineers once expected diffusion-limited transport to dominate. Instead, droplets display active internal flows that enhance reaction rates. This enables faster biochemical assays, nanoparticle synthesis, and crystallization control. Microfluidic reactors rely on these effects for efficiency. What seems a paradox is turned into opportunity. Mixing in laminar worlds expands technological horizons. Droplets reveal hidden power in surface forces. Digital PCR uses microdroplet mixing to accelerate amplification without mechanical stirring. It is like discovering a hidden motor in what looked like a still toy. The paradox highlights the importance of interfaces in soft matter systems. Bulk scaling laws neglect interfacial gradients, yet these dominate at microscale. Mixing emerges not from turbulence, but from active surface stresses. This redefines how order and disorder arise in fluids. Small scales magnify effects invisible in bulk systems. Physics at the edge becomes physics of the whole. The paradox teaches humility about scaling laws. Interfaces can create complexity from simplicity. Soap films display Marangoni flows that stabilize or destabilize film thickness. It is like a stage curtain that suddenly drives the play instead of just framing it. The paradox is that laminar flows, predicted to scarcely mix, often display vigorous internal circulation. Marangoni stresses, evaporation, and solutol gradients convert passivity into activity. Droplets that should remain stratified become efficient mixers. The boundary between order and turbulence blurs at small scales. What should be static becomes dynamic. What should be slow becomes rapid. This shows that laminar does not mean lifeless. Interfaces are engines hidden within stillness. The paradox reveals active worlds in seemingly passive droplets. Sessile droplets on heated surfaces mix dyes vigorously despite re-1. It is like finding a lively dance hidden inside a silent room.